Okay, so in this lecture, we're going to talk about soft margin classification. In the hard margin classification problem, we have to talk about the situation that the data can be perfectly separable. But if the data looks like this, as we said, we have some outlier right here. You can see there is a blue point right in the cluster of the red point right here. Although this point can be linear separable, but there will be a very narrow margins. So basically, if this is my decision boundary, that won't be a very good choices. I would rather to have a large margin solutions, but even with the 1 point is I mean being like misclassified. So that means I can allow certain errors, but I still want to keep as much large margin as possible. So this is the goal for the soft margin classifications. Okay, so let's go back to the math. Okay, so the goal is keep like large margin solutions even though some constraint is being like violated. So that means we can allow to violate certain constraints. So that means we need to reformulate this problem a little bit. And also this is, so meaningful and the situation is, and this is particularly useful when the training data it's not linearly separable. That is totally possible. Think about this data set. You have a 784 dimensions. This type of data set is impossible to have a linear separable in the dimension of 784. So, and what we're going to do is we're going to introduce something more. So here's what I'm going to do. So I'm going to introduce additional variable, introduce slack variable. So what does this variable do? I'm going to call it Kasi. Kasi is also in Rn. It's a vector that allow misclassification for some outliers. So as far as this misclassification rate is low, that is also fine. So that means previously in the hard margin, hard margin constraint is my yi, xri, w plus w0 should be bigger equal than 1 for all I. All right, so what I'm going to do is I'm going to relax this constraint and the relax constraint. So this is becomes soft margin constraint. So that means we allow certain situation that this and this hard constraint can be violated. The way to go and do it is we introduce that select variable, that my constraint becomes the following. I'm going to keep the same color to indicate this is being the same. So this is bigger equal than 1, but I'm going to subtract the c of I right here, and with c of I is bigger equal than 0. Okay, so this basically we introduce a new quantity that is possible that this c of I, and with this some c of I and bigger than 0, that can allow my data xi and yi can be violated this and like hard margin constraint. In particularly, if the c of I is precisely bigger than 1, that means I don't have the situation that these two and yi and my predictions have the same sign. I only have and have some, and it can be negative. So, and what does that mean is my yi and my prediction right here. So these two things can have a different sign. So what does that mean? That implies that the x of I is misclassified. So as you can see, this is still allowed. If the c of I is between 0 and 1, then this constraint is still, and this multiplication of this whole term is still bigger than 0. That means they still have the same sign. That means the classification is correct, but x of I is within the margins. So previously we assume the margin is something that is cross this two and multiple supported vectors, and then there will be no point within the margin because that's a point of hard margin problems. So there will be no point so between these two margins. If we allow this and the c to be between 0 to 1, although this could still be and correctly classified, but this point will be within within the line of these two margins. So and what does that actually mean in terms of plot? So for example, we have, I think we're using the red and blue, right? Okay, red and blue. Red. And then we have blue. And then this is one more red right here. So my decision boundary is something like this. I would say, let me get one more blue right here. So my decision boundary right here is, could be something like this. And my margin is like that. Okay, so the situation of this point right here, it's still being classified as blue, right? So I mean, this is situation that this c is between 0 and 1. That means this point is actually within the margin, but still being correctly and being predicted as blue. However, this point right here is the situation that c, at that point, is actually bigger than 1. So that means it already, and not only, cross the, so cross the margin line, it also crossed the boundary lines. And that indicate, so this point will be and misclassified as red. So under this situation, and when the c of I is bigger than 1, and that indicate this point is just being incorrectly and classified. So you can think about this is, and this line corresponding to c is between and equal to 0. This is and corresponding to c equal to 1. And for the color of and for the color of the blue, situations. So and everything here will be c equal to 0. Everything here, this will be c is between 0 and 1. And everything here, this will be c is bigger than 1. So these are the regions, and gradually and progressive. Okay, so as I said, if c is bigger than 1, this will be the cases that you have, basically misclassifications. Okay, so then this and optimization, and of course we don't want this and c and to be large at all, and that means we also want to minimize the c as well. So and we don't want this c to be large. If the c is large, that means there will be a lot of and a point being like and misclassified. So so let me just compare with an objective here. So my objective, so I want to compare with hard margin and soft margin. Of hard margin is I want to minimize my W in R D and the W0 in R and the c in Rn. So these are, so sorry, that's just being hard margin, so I don't have a c here. So this is 1/2 W square 2 norm subject to the constraint, this yi of xi W plus W0 bigger equal than 1 for I is 1 to the n. So this is for hard margin. So for soft margin, so what I'm going to do is I'm going to keep everything that we have the same for hard margin. So we still have trying to minimize the square norm of the and the square of 2 norms of W, but I need to add one more term, which is lambda of summation of I from 1 to the n of c of I. Why? Because we want to and ensure this, and we have like less and the misclassification rate is being minimized as well, and also subject to. So we have a same part, it's the same, but we allow some and the misclassifications. This and this becomes 1 minus c of I right here, and also c of I is bigger or equal than 0 for I is from 1 to the n. So these are the differences between soft margin and hard margin. All right, so this is extremely important. All right. So let me just rephrase things a little bit. So this lambda is predetermined some regularization parameter. You can think about this as actually some like and regularization, and you actually need to balance between the square, and the square of the weight and the versus sum of the and the c right here. And you can also think about this. So the first thing is like lambda is bigger than 0 is some regularization terms. And also you have some meaningful thinking is this c of I divided by the norm of W is actually the distance between x of I and the corresponding bar and corresponding like and the margin and boundaries. So this is the corresponding margin boundary is x of W plus W0 equal to the corresponding margin boundaries. If it is 1, that will be 1. If it is -1, that will be -1. So this will be just yi. So this is corresponding to margin boundaries. Line. Right, so think about this way right here. So for blue point, this is the corresponding margin line right here. So if you have a point right here, so this will be the distance between the point between this like corresponding margin line, and this will be c of I divided by the norm of the W right here. So this distance right here is equal to c of I divided by the norm of and the norm of W here. And of course, if this point doesn't like cross the bar and the margin boundary, so this will always be 0. So it's on the correct and the side of the margin boundaries. So this distance only makes sense if you go cross this bar and the margin boundaries. Then we need to calculate this distance. Okay, so if we have a small lambda here, so that means that will encourage like large and the large c. So that means I allow and encourage the misclassifications with large margins. So that means encourage. So this is basically a balance between misclassifications and the large margins, right? So, and if we allow the small lambda, this means we are going to encourage the misclassification with the large margins. If we have large lambda, that means we are going to encourage the small c vectors. And as a result, we're going to discourage the misclassifications with the narrow margins. So basically, this is actually a balance between misclassifications versus last margin and with the large margins. So this parameter lambda here is actually tuning around the balance between these two factors. And of course, if we think about this is the very extreme cases that lambda equal to infinity, that just indicate my C of I just being 0 right here. That means I allow no misclassifications. So misclassification. So one way to work with on the hard classification is we solve for the misclassifications, but then we put the lambda is super large. Okay, so you can solve for the due problem as well. So due problem, I'm just write it down. The due problem of the soft margins. So the due problem of the soft margin. Let me see. Okay, so the due problem of the soft margin is, is following. So everything is, basically the same as hard margin. So this will be maximum of alpha in the Rn, summation of I from 1 to the m of alpha I, subtract 1 over 2, summation I from 1 to the n, j from 1 to the n, and yi, yj, and the alpha I and alpha j, and x of I, x of j, transpose. So this is precisely the same objective that with hot margins, and subject to that summation that I from 1 to n of alpha I, yi equal to 0. This is also the same. And the alpha I is bigger than 0. The only difference is you need to set less equal than lambda for all I from 1 to the n. So the due problem of the soft margin is nearly the same. Just the only thing is we add the upper bound for alpha I. That upper bound has to be lambda. Okay. So we can compare with this due problems versus the primal problems here. So the primal problem here, I'll say in primal problem, we also need to solve for the Cassi of as a vector of Rn, right? So for the primal problem, we have m plus d plus 1 unknowns. Okay. And we have n linear inequality constraints. And mixed with all these and x, I and yi. And non-negative constraint because the Cassi of I has to be bigger and greater than 0. Then this whole problem is convex quadratic. Program. Okay. For due problem, right here, it's n unknowns. So this is smaller. I mean, number of unknowns is smaller than the primal, because primal we have a d plus n plus 1. And we have one linear and the linear equality constraints. So if it's one linear equality constraint, and this can be very easily removed. And we have a n box constraints. Okay. And also, this whole thing right here can be written as as a matrix form. So this is and the objective can be written as as follows. It's minimization of alpha. It can be written as 1/2 alpha transpose G alpha minus 1 and column 1's transpose of alpha. So this G ij is nothing but yi, yj, xy, and xj transpose. Okay. So this is called G right here. It's called a Gram matrix. You probably have heard that before. And particularly that will be a positive definite matrix. And they can be, and the reason why this is positive definite matrix, because this can be written as G is VV transpose, with V is equal to Y1, X1, and so on, Yn, and X of n. So this is written as follows. This is the Gram matrix. All right. Okay, so again, we can solve this problem, and the way that we solve it is you already see that in the the previous one is in the hard margins. So this is how we work with a soft margin SVM. Wait, right here. Where is it? All right. So the difference is here is we need to add the constraint, which is here we call it C, right? So this is actually the difference is here. So we need to stack with and we need to make sure this is bigger than 0 and smaller than lambda. And the way we do it is we create a matrix of A, which is minus identity, and we stack like and minus identity and a vertical stack with identity here. And correspondingly, B as on the top will be a bunch of zeros. The bottom will just be C's and the columns of C's. So which is in this case it will be lambda. So the only difference is here that we changed is we changed this inequalities and to ensure that we're making this and the condition is to be alpha is bigger than 0 and less than lambda. In this case, it's C. That's the only differences that will be, and we're making here. Everything else is being precisely the same. This is exactly what we are working for the soft and the soft margin SVM. So you only need to change a little bit for the hard margins. It turns out and can be and work out for and as a soft margins. All right, so as you can see right here, we set C equal to 1. And as this result, and we can find out these points are being a supported vector. And this point right here is being considered as being violations, because it goes beyond the subdivision boundaries. So these are the points right here. So this gives you like whole idea how they solve this problem. Here we just said, I believe, set it like C or lambda equal to 1. So we can see there are like bunch of points here, and so there's a 1 point right here, and actually didn't violate the division boundaries, but still within, still go beyond the margins. So for this point right here, the Kc of I will be and it will be bigger than 0 but less than 1. For this red point right here, this Kc of I will be bigger than 1. So that means we already make the classification errors. Okay, so this is quite. If you can understand hard margin, this soft margin things, it is quite straightforward. Okay. So let's go back. Okay, so but that's not the end of everything. So the reason why we want to still continue is because we want to have a different perspective of the problems. And for example, right here, so let's step back to rethink about perceptrons. So I'm going to go back to the math. So let's go back to perceptrons. So so I want to remind you, and you can like think of things a little bit. So let me just go back to perceptron. Then we have a data set that D is X of I and Y of I from 1 to the n. But in this case, I'm going to call this Y is between +1 and -1, just to be consistent with SVM. And perceptron, we're using some like step function, right, as our activation functions. So this is, I'm going to change into, if it is 1, then if Z is bigger than 0, that will be 1. If it is Z is less equal than 0, then it will be -1. So in some senses, what we are trying to do is we are trying to minimize this misclassification situation that we are trying to summation from I from 1 to the n of this indication function of yi of x of I w plus w0 is less than 0. This w is in Rd and w0 is in R. So this is basically the misclassifications. So basically, I want to count whether this is being misclassified. If it is misclassified, then I'm going to add 1. And otherwise, I'm going to, it's like correct, and as I'm going to add 0. So this indication function right here, so this is and the loss for perceptrons. So this is, I mean, so essentially we are working on this kind of problems. And this is equivalent with what we already did in the homework, sorry, in the, previous lectures that we are working with. Yi minus phi of mx of I w plus w0 then square. So these two things and these two laws are kind of equivalent and equivalent. If they classify correctly, then this component inside that will be 0. If the classification is wrong, then this point inside that will be non-zero. I believe that will be +2 or -2. Then if we take the square, that would be just 4. But in this case, it's for the indication functions, that would just add 1. So the only difference is this is loss times 4 will be exactly equal to the loss functions of the mean of the square error. And of course I need to define the indication functions like this. So this indication function is 1. For the condition that if z is less than 0, it is 0 otherwise. All right, so this gives you some idea, what we are working with. So this whole thing right here, you can think about this whole thing as a 0-1 loss. Right? But this, 0-1 loss and this optimization problem, we are just rewriting things around. It is, very difficult, very hard to optimize. In fact, that's nearly impossible. Why? Because this, whether it's indication function or step function, they are discontinuous. They are non-convex. They are non-uniqueness. So it's non-convex. It's discontinuous. And non-uniqueness of the global mean. So basically, there's no way that you can do this and calculate gradient and calculate everything with a gradient descent. But of course, we can use something called fake gradient, similar trick that we did. But this just gives you some idea that the loss function that we had before can be rewritten in a way that looks like indication functions. So can we actually rephrase this primal problems right here into a different ways? So yes, we can, in fact. So the way that we can look at that is the following. If we look at this constraint right here, we can and move this c of I to the left and everything here to the right. So that means my c of I should be bigger or equal to 1 minus yi and x of I w plus w0. And also my c of I has to be bigger or equal than 0, right? So that means I can just rewrite things is my c of I is bigger or equal than maximum this quantity and 0. Right, so this is basically, we can rewrite everything terms of different ones. Okay, so my primal problem we can rewrite everything as minimization of still W in the D, W0 in the R, and the c of Rn. I have a 1/2 square of 2 norm of W plus lambda of summation of I from 1 to the n of c of I. And in this cases, my constraint is combined subject to my c of I is bigger or equal than the maximum of 0 and 1 minus yi x of I plus W0 for all I. So and the key here is if 0 is bigger than 1 minus of this whole term, that means all we need to do is, and we can just simply choose c of I equal to 0. Right, because that's the minimum that we can choose. That means my x of I is on the correct side. Of margin boundaries. So that's also indicate the whole condition is fully satisfied. If 0 is less than equal and less than this quantity, so that means I'm going to, that means I'm going to choose c of I is equal to 1 minus of, because this is, I want to minimize the c of I, but, and with the, constraint of c of I has to be bigger than the maximum of these quantities. So, and why not just simply choose that c of I equal to this maximum of these two quantities. So if we choose c of I to be that, and that specific values, that is the minimum that we can choose for the c of I, that indicate this, and x of I is on the wrong, side. Right, so this is kind of a very interesting way of rewrite everything. But with this result and rewrite, we have and we observe my c of I can just simply assign c of I as maximum value of 0 and 1 minus of yi and x of I w plus w0 for all of I. So that means we actually can drop the constraint just to replace this c of I with this expression. And that actually turning from the constraint optimization into an unconstrained optimization problems. So this, we turn constraint optimization into unconstrained optimization problems. So you can see this is very significant. So what we are actually getting is our primal problem becomes the following. It becomes minimization. We get rid of the casino. Then we have a lambda of summation I from 1 to the n of maximum of 0, 1 minus yi and x of I, w plus w0 plus 1 over 2 square root 2 norm. So what we are trying to get here, you can think about this and actually think about this as a loss. Because if you remember, the mean square loss also has this kind of form that is I from 1 to the n of yi subtract to phi or f of x of I of theta of square. So this is the mean square error. But here in the middle, we have a different type of error. So this kind of error is like this. The error is maximum of 1 minus z and a 0. So this is called hinge loss. So you can think about, I mean, if you actually plot this out, looks like this. So the hinge loss looks like, if this is 1 right here, it will be like that. Okay, so this is your z. So this is your hinge loss. The 0, 1 loss says it looks like this. It will peak to be 1, then drop into 0. Add 0 right here. So this green line was, the blue line is 0, 1 loss. This red line is the hinge loss. So hinge loss actually depends on how far, this example is from this decision boundaries. If it is on the right and the right side to the decision boundaries, that would be 0. If it is not, that would be just assigned to 1 minus and the 1 minus z, right? So this just depends. If it is very far away, that is away from the decision boundaries, and this value will be larger. Okay, so you can think about right here is a convex relaxations of my 0, 1 loss. Okay, so hinge loss is actually a convex function right here. So this whole thing right here, we get rid of the constraint. The beauty when we get rid of the constraint is we can use the gradient descent. In this case, in fact, we can find the gradient now. Although this is not fully differentiable at anywhere, but can be solved by separate gradient method. So, and of course, this is also equivalent to write as the following. I'm going to move this lambda to the into the part of square norm of lambda. So this and it can be written as the following: the sum 1 to the n, maximum of 0 of this whole term, plus 1/2 lambda square the 2 norm. If we write this way, this is very, very close to the ridge regression. But the difference is my loss right here is I'm using hinge loss, but plus some L2 regularization. So this is the hinge loss plus the L2 regularizations. So softmax, the soft margin SVM, it's equivalent with we take the hinge loss plus the L2 regularizations. But in this case, is this lambda, it's kind of the opposite of the first lambda that we have. Okay, so I mean this has a different way to interpret that, but that is okay. Okay, so with a different picture view actually can help us to have a better understanding of these problems. Okay, so this is the first part. The second part is we actually will calculate this subgradient, and that we are going to implement everything from scratch.